Yesterday we saw some general properties of 6-dimensional SCFTs and little string theories. Those properties are not rigorously proved within the context of SCFTs or little string theories, but they do occur in all the examples that we know so far. So I want to classify these theories in a field theoretic fashion. So yesterday we saw that SCFTs and little string theories have a tensor branch of vacua on which we obtain a non-abelian gauge theory coupled to some tensor multiplets. So we know, since we know some things about gauge theory, we can try to use gauge theoretic methods to try to classify these theories. So right, so let me give you an overview of the classification, and then I will move on to F theory, where you can classify all sorts of theories which are not in the gauge theoretic classifications as well. Okay, so let me assume that that each string in my, so strings are in correspondence with, so
this viewpoint is similar to the one which says, which would say that in 4 dimensions, if I classify all abelian gauge theories, then I have classified all n equals to 2. For abelian n equals to 2 gauge theories, then I classified all n equals to 2 gauge theories, right? Because that's the Sackler-Witten picture, which is essentially that's
right,
we're
right.
also choosing to go to a particular
Right.
vacuum and then classifying the low energy physics there, right? But yeah, in other words, would classifying low energy physics be sufficient to make a claim about classification of theories themselves?
So all the classification procedures are based on classification of tensor branches. What I'm going to do is to assume some restrictions on the tensor branch itself in the gauge theoretic classification, because I want gauge groups to appear for every string. I don't want any strings which are not the instanton strings. So right now I'm going to assume that all of the strings are instanton strings.
So it's classification with a bunch of caveats.
Yes, with a bunch of caveats. A Lagrangian classification, sort of. Okay, so I assume that all strings on the tensor branch are instantons. So this means that the number of simple factors in my gauge group will be equal to the number of strings and so at low energies we will see a non-abelian gauge theory whose instantons are coupled to the tensor multiplets, are charged under tensor multiplets. Right. So this is the idea on which this classification is based, and so let me move on to. So let me tell you first some things about Lagrangian multiplets in 6-dimensional 1,0 supersymmetry. So what are the n equal to 1,0 multiplets? So the low energy theory will be comprised of some of these multiplets interacting with each other. So first of all, we can have a vector multiplet, and this contains a gauge field. Let me denote it by So this is in the adjoint of the Lie algebra, and it contains a fermion which is in the adjoint of the Lie algebra, and it transforms under the R symmetry, USP2 R symmetry, and under is a chiral fermion. Okay, so notice that there are no scalars, so there is no Coulomb branch in 6 dimensions. Okay. Another multiplet is a half hyper. And this contains some complex scalars which transform under USP2 as a vector, and it transforms under the Lie algebra in some representation of Lie algebra, which is symplectic. Right. So this means that we again have an invariant tensor which is antisymmetric. So I have something like an omega AB. Okay. So again, I can just as I did yesterday, I can use this invariant tensor of this representation along with the antisymmetric invariant tensor of the USP2 to make a Majorana condition, to impose a Majorana condition on this. So in the half hyper, I have actually imposed the Majorana condition.
So that means that you have the representation and its complex conjugate, and then they combine together somehow. So what does it mean symplectic? Give me an example.
So
SUN, suppose your gauge group.
for SU2, the fundamental representation.
So for SUN, if you
For
have a fundamental, would you also need to have an anti-fundamental?
No, so it's not for SUN. I'm saying.
A
So-
is the gauge group index, right?
So capital A is the representation index.
Of the gauge group.
Yes, it's a particular representation which admits an invariant tensor, an antisymmetric invariant tensor.
So suppose the gauge group was SUN.
Then I don't know, I don't think there are such examples. For SU2, there are many examples. So for SU2, you can have, so let me label them by the dimensions. Then you can have 2, 4, 6, and so on.
Those are representations that by themselves satisfy a condition. But surely you can combine a representation and its complex conjugate and satisfy a condition.
Right. So I'm saying for this representation, I'm looking at a, right.
So you
I'm not doing
for
so.
SUN you could have a fundamental and an anti-fundamental presumably and combined.
Right.
In this notation, there will be 2 half hypers.
Right. I mean, so
Right, but he didn't say irreducible representation. So I mean I think that when you say symplectic representation, then you need to make it non-irreducible.
No,
In some cases.
yeah. In some cases,
Some cases it's fine. Some cases.
symplectic and irreducible.
Yeah.
Right.
That's the one.
okay. Then you can have a tensor multiplet. This contains a 2 form.
Realistically speaking, what kind of gauge groups would you be having?
All sorts of gauge groups. I want to just classify
So even
everything.
SUN, right?
Yeah.
Even SUN.
And
So
basic
in that
gauge.
case, you would need what?
Right, yeah, so let me talk about a hypermultiplet as well. I just wanted to write everything in the most general terms. So you can have a hypermultiplet in which
Oh, I see.
which is just a half hyper
It's a complex.
in R plus R bar. So R plus R bar admits such a invariant tensor. So this will be hyper valued in R in the usual terminology. So the reason I'm writing this half hypers is because I mean, because of you can have half hyper multiplets, right? So if you have, you can have. So if you have SU2 fundamental of SU2, you need not have a full hyper. You can have half hyper sometimes. And I want to allow the most general case. Okay. Then finally, you can have a tensor multiplet. This contains a two form such that the corresponding field strength is anti-self dual. And it has a real scalar phi and a chiral fermion, an anti-chiral fermion. So it has fermions in it. So I forgot to write it down. Right. So it has some fermions, anti-chiral fermions.
And just for some equation like that, are you going to use the half hypers? Yesterday you had the Dinkin diagrams. So you're going to put the half hypers at the end. You have the non-affine case. Is that roughly that line?
Half hypers can appear even in the middle.
Okay.
Right. So if you have a SO times a USP gauge group, you can have half hypers in the bifundamental of this. Okay. So now we see that all sorts of chiral and anti-chiral fermions appear in these multiplets. So if you write down an arbitrary theory, gauge theory, then it will have some anomalies, one loop anomalies, which can spoil the consistency of the theory. So we just have a gauge theory, so we just want to look at the gauge anomalies and the mixed gauge gravitation anomalies. So let me write down the anomalies for each of the multiplet. So for vector, I will write down the anomalies in the form of an anomaly polynomial. So the anomaly polynomial takes the following form in an appropriate normalization. So this is the pure gauge anomaly part, and this is mixed gauge gravitation anomaly. R is the Ricci tensor. Okay, and a half hyper. So let me write it down for full hyper. For half hyper, you just take half of it. So for a full hyper, you have 2 by 3. So here I'm taking trace in the adjoint representation for vector multiplet, and here trace in the representation for the hyper. Okay. So the vector and hyper just differ by a sign and the trace. Okay. Right. So it turns out that these are not the one loop anomalies are not the only anomalies that you can have in 6-dimensional gauge theories. You can also have Green-Schwarz anomalies coming from the coupling of tensor multiplets to the gauge theory, to the hypermultiplets and the vector multiplet.
How about overloop anomaly coming from the side? Fermion, chiral fermion, the tensor multiplet?
Yes, uncharged under gauge group, but gravitational. But gravitational, there's no RQ.
So there is no mixed. I mean, there are things, but I'm dropping them. So there are anomalies related purely gravitational anomalies, but since I'm doing field theory, I don't care about them. Okay. So the way that tensor multiplets couple to the rest of the theory is through this fact that all of the instanton strings are charged under tensor multiplet. So let me do the analysis for a single gauge group only, and the extension to multiple gauge group is straightforward.
There is also an assumption that the gauge group does not have U1 factors.
Right, there's this assumption.
I think the anomaly polynomial is could have more terms because you could trace as only trace that square.
Right, so I think if you can include U1, but you won't be able to satisfy anomaly cancellation if the U1 couples to rest of the theory. It should appear just as a decoupled free U1. That's why that is a reason for why I'm not including abelian. I mean,
And just add a term corresponding to the anomaly.
you can do that, but you cannot have this one. So the cancellation of the other parts is violated. So you can add trace to f, trace f, but that does not affect the other things, I think. Okay. Right. So the instanton strings are charged under the tensor multiplet.
What sort of mixed flavor gauge anomaly would also spoil the theory?
Flavor? No, it won't. It will just spoil the flavor symmetry.
All type of things. So
Now, if I have flavor gauge anomaly, right, I can either keep the flavor symmetry and spoil the gauge symmetry. Then I will spoil the theory. Or I can keep the gauge symmetry.
multiple things, right? So there could be one F flavor and 3 gauge flavors. Right?
Okay.
Trace F gauge cube, trace F flavor. That's it. So even that.
Right. So I can just say that I don't have flavor symmetry and I won't turn on its background. Then I won't see those
Then
anomalies.
why do you need to cancel gauge gravity anomalies?
Because I want to put my theory on an arbitrary curved manifold.
But if I don't want to, then it's fine.
Yeah, then it's fine. Okay. So the fact that the instanton strings couple to tensor multiplet means that
Sorry, that means that you should also cancel pure gravity anomaly if you want to put the theory on.
no, I don't want dynamical gravity.
Sorry, yeah, go ahead.
Okay, so right, so the fact that the instanton strings are charged under the tensor multiplets is equivalent to the following statement. And because of Dirac quantization, this coefficient has to be appropriately quantized. Okay, so now if I use self-duality of H3, then I obtain an equation, the following equation. And this follows from a term, this looks like an equation of motion for H3 and follows from a term in the Lagrangian, which is of the following form. So I have my Lagrangian will look like a gauge part, of Lagrangian for free tensors minus this contribution. And this was the coupling I was describing yesterday. Okay. Now, notice that if I have to satisfy this equation, then H must cannot be dB, but has to be modified. So it has to be modified by a Chern-Simons term. If you take the exterior derivative of Chern-Simons term, you obtain the instanton number. Okay, and now let me do the usual trick of descent in anomalies. So this implies that delta H under gauge transformations. So if I take a variation of H in with respect to gauge transformations, it must be 0. And this is also equal to dA of delta B plus C times delta of Chern-Simons 3, which I can replace by D of some lower dimensional form. Let me call it CS2. Okay. So this would imply that delta B is going to be minus C times this form up to exact terms. Right. So what does this mean, right? So this means that B transforms under gauge transformations.
What about the winding terms in CS3? If you do it, change it by gauge transformation.
I'm just looking at the local part of the. I'm just looking at all of the analysis is done locally. What happens at a point? Okay, so this means that B transforms under gauge transformations, and you clearly see that this term is giving you an anomaly. So you can read the anomaly. There is an anomaly, Green-Schwarz anomaly, which will be C squared Chern-Simons 2 wedge trace of F. And now you can just use descent to find the anomaly polynomial. This will be simply C squared trace of wedge F squared. So what do I learn, right? So the Green-Schwarz anomaly is never has a very special form. It cannot be quadratic in F. It has to be so. It cannot. It's not. So in 6 dimensions, you have the following characteristic polynomials in general. You have trace F to the 4, and you have trace F squared squared. If I look at Casimir invariants of degree 4. And so this means that the Green-Schwarz can only be of this form and never the purely quartic piece. So the gauge theory must be such that the purely quartic piece cancels by itself, and then I can choose a coupling to tensor multiplet to cancel the quadratic piece. But the quadratic piece has to be positive definite because of this C squared. So there are two restrictions on the kind of gauge theory that I want to have. So this must be 0, and the coefficient must be negative definite.
Sorry, I didn't quite understand how you intend to cancel the
Sorry?
trace F squared piece.
By choosing an appropriate coupling.
But that appears there as C squared, as you say. So
Right. So if suppose my gauge theory gives me minus C squared of this, right?
But that's
Then I can cancel it by.
no, but here it seems that these matter multiplets are not contributing trace F squared term. No.
They are contributing because you can break this trace rows into
Oh, okay, sorry.
traces.
Representation. Yeah, okay.
So here the trace is in a particular representation.
Right. So that's adjoint trace, right?
I mean, if you it depends, right? If for SU you will want to choose, if you want the minimal instanton, that comes from trace of fundamental. For SO, it's half of the trace of vector representation. There are some group theory factors here in this trace.
Can it be absorbed inside C in a different way of looking at it?
Right.
If you say C is not exactly.
Yeah, but then the quantization condition will be different for different groups.
C is not entirely from physics, then it can be reabsorbed. All these extra group theory factors can be reabsorbed.
Mm-hmm. Okay. Okay, so this leads me to the consistency conditions I need to impose on my classification. So most of these were found by Seiberg, except the quantization condition, which was added later on. I don't know who first added the quantization condition. So I'm writing them in general. When I have multiple gauge factors, the conditions are as follows: that the one loop anomaly must factorize into a negative sum of perfect squares. So you can have things like at minus alpha trace fi squared. So alpha some ai trace fi squared minus beta bi trace fi squared, right, and so on. Something like this. Okay. Yeah. Now you see, right? I will add things like I will add tensor multiplets, which will couple to this part, and the other part. I will add as many tensor multiplets as the number of perfect squares in my anomaly polynomial.
So how are the two terms different?
I mean, I'm just saying that it's a sum of these things, sum of perfect squares. A sum of perfect square need not be perfect square.
Right, but I'm just saying, so what is I?
It's a label for the different gauge groups.
Particular group.
Right.
So you're saying different multiplets will give different contributions of this kind to the I?
I'm saying that the whole contribution, if it factorizes it should factorize like this.
From the matter.
Some linear combination of trace fi squared times some negative coefficient.
AIs are integer, AI, BI are integer.
Appropriately integers because of the quantization condition.
Alpha, beta.
Right, I mean, okay, alpha times AI has to be appropriately integer.
So you're saying this because you want to cancel Green-Shor's anomaly, is that right?
Right. So this is coming from Green-Shor's, and the quantization is coming from the fact that from Dirac quantization. Okay. Okay. Another condition which I did not talk about at all is that the global gauge anomaly should also vanish. Must vanish.
I don't understand how you would interpret alpha. So in order to cancel that, you would write a coupling of the type AI trace fi, let's say first term only.
Right.
AI trace fi squared b.
Let me just absorb alpha inside, right? I can do that.
Yeah, alpha and beta are possible.
Right.
Now the quantization is
For the AIs and the BIs. So even if your theory does not have any anomaly seen in the anomaly polynomial, you can still have the gauge theory might still not make sense. So this is because the standard anomaly polynomial only captures anomalies under gauge transformations which are connected to the identity in pi d of the gauge group G, where D is the dimension of space-time. So I can still have non-trivial elements. I need to cancel anomalies for non-trivial elements of pi d as well.
that's
So-
where we will come about non-correct, disconnected.
Right. And in 6 dimensions, this only affects gauge groups SU2, SU3, and G2.
Could you connect the argument once again to the global? The pi d argument with the local part.
No, this
No.
is a different thing. This is global.
Yes.
No, I'm just saying that the anomalies captured by the anomaly polynomial are in the identity component of pi d.
Okay.
It should be phi, okay, so
Pi 6 is space-time dimension.
So you're saying these are the only Lie groups for which pi 6 is non-trivial.
And there is an anomaly. So anomaly is given by the determinant of the Dirac operator. I mean, you want to see how Dirac operator behaves, right? I mean,
So even if pi d is non-trivial, there could be that you just cannot write.
it might be that the fermions do not have anomaly under those gauge transformations.
So how do we get pi 6? If we take 6-dimensional space-time,
Right.
the thing at the boundary is S5.
So the gauge transformation approach identity at infinity.
Okay.
So obtain a map from S6 to G.
Sorry, the boundary is S5, and usually I want something that binds around.
No, the whole space-time is S6. I'm looking at maps from space-time to,
So your space-time is S6, is it?
it's R6, but the gauge transformations go to identity at the boundary.
Because usually for instanton physics, we take S3 at the boundary. Look at maps of S3 to
Right.
And
So this is a different thing. I'm looking at gauge transform. So what is the idea, right? I want to see whether the partition function of chiral fermions changes when I do gauge transformation. A gauge transformation is a map from R6 to the gauge group, and I want to consider only those gauge transformations which go to identity at the boundary, at infinity. So a gauge transformation is an element of pi dg.
And you could say that you want to make it consistent on S6, right?
Right.
that's the same state.
Yeah.
Right.
Because if it all goes to 1 at infinity, then you can compactify it
Mm-hmm.
and make it S6.
Right. Okay, and then there's the quantization condition that these coefficients have to be quantized. Okay,
Sorry, so the 4-dimensional analog of this would be pi 4 of SU2 is Z2.
Right, right.
That was written somewhere.
Okay. So now, these are the consistency conditions on your gauge theory, and now you can proceed and do the classification. You can look for all sorts of gauge groups and matter content which satisfy these three properties. So some vectors and hypers which satisfy these properties, and the classification. So I won't go into the detail of classification. It can be found in the following papers. And the classification for simple gauge groups was already done in the second superstring revolution, which can be found in this. It's a paper by many Swedish physicists. I don't want to write down all the names.
But here also, presumably, so this is a general classification in this framework. There is no assumption about the quiver being linear.
No, general classification.
Right, fundamental matter, all sorts of representations.
Everything. Yeah.
You also classified n equals to 2 theories, right? In
Right.
QG.
Right.
Is there any commonality?
Some similar things appear, like, I mean, how familiar are you with the class n equals to 2 classification? I mean, there's nothing, as far as physics is concerned, nothing is, and it doesn't matter really.
So let me, maybe it's not too useful, but let me ask you this. In n equals to 2, from the classification, are there hints that there is some sort of a Riemann surface underlying the classification?
In the n equals to 2 classification, that's just a beta function classification. You just want beta functions to be.
From there, do you see, graphs of some shapes which are essentially, is it tied to Gauss's classification somehow?
No, I don't think so.
So I was wondering whether there's any geometry underlying this classification.
Mm-hmm. I mean, so the gauge groups come from the necks of the Riemann surface, but the matter comes from various punctures, right? You can build Riemann surfaces for it in the same fashion, just the same dictionary.
Physically motivated.
Okay. Right. So let me discuss some more parts of physics, which follows from this Lagrangian considerations. So let's discuss the tensor branch of vacua under this assumption. So recall that we had a term in the Lagrangian of this form. Now, if I supersymmetrize it, I obtain a term like this. And this really means that the Yang-Mills coupling at a generic point of tensor branch is actually the tree coupling plus the wave of phi. Here phi is the scalar in the tensor multiplet. So the effective coupling is actually governed by this.
Sorry. I think I can phrase my question better. From string theory, we see that, as you explained before, that the quivers that you get are linear quivers,
Mhm.
right? Essentially, NS5 brains playing on the concept line monopole.
Right.
So there is no signature of that linearity in this classification of the quiver.
I mean,
you have many gauge theories which would.
so I was considering some examples in that in those cases. Those were some linear examples which are realized in this classification
Right.
as well.
But let's say, sure, those are realized, but there are presumably other more complicated
Right.
theories also that come
Mhm.
about, right? So if one were to ask, is there a string theoretic origin of those theories?
Of these theories?
Yeah, of the general 1-0 theories.
So of the Lagrangian ones, the ones I've classified here, they all have a string theory origin.
Okay. Or maybe that's the F theory thing that you want.
Right. But in F theory, you obtain more theories where you have strings which are not instant-on strings. So an example is 2,0 theory. All the strings, none of the strings are instant-on strings there. Okay. Right. So now the fact that the instantons couple to the tensor multiplet implies that the charge of instanton is actually goes like C times the instanton number. And if I have a BPS instanton, I can just predict its tension. Then it must be the instanton number divided by the Yang-Mills coupling squared. So this goes like C squared times the wave of phi. So you see that in this class of theories, you can actually prove that the tension of the strings is governed by the tensor branch modulus. Okay. Since I didn't discuss the classification, let me discuss two short examples where we will see these three things being applied. Okay. So the first theory that I want to consider is this one. This is just one of the linear chains that I was describing yesterday with just one node, one gauge node. So this is an SUK gauge group with 2K fundamental hypers. And let me assume that k is greater than or equal to 4. So if I just compute ith one loop, I obtain something like so here trace, when I write trace, I mean trace in fundamental. So you see now for these SU gauge groups, you can write down the trace in adjoint of f to the 4 as in terms of the traces of fundamentals as a following linear combination of traces of in fundamentals, and trace f squared as like this. And now if you just plug this in, you find out that ith one loop is -4 times trace f squared. And this is negative definite. So this satisfies the first condition. Also, because this is not SU2 or SU3, this satisfies the second condition. And now we have to see whether it's appropriately quantized. So let me just tell you the result, what the quantization in this case, for the case of SU4 is, SU greater than or equal to 4 is. So for these gauge groups, the quantization condition implies that your one loop anomaly polynomial must be -2 times an integer times trace f squared. And so you see that the third condition is also satisfied. So this is a theory which falls into this classification, and we saw yesterday that there actually exists a 6-dimensional SCFT whose tensor branch is this.
But there was also a statement about perfect square.
Right, it's already here. There's just one gauge group.
You don't want the coefficient to be perfect square because there is a c square there. So c is something that is quantized, and that thing that appeared was c squared.
Right.
But your quantization condition there for the anomaly polynomial does not have that flavor, right? You are saying that hash is a number, integer, right?
Right.
Not integer squared.
No.
So
No, c was not an integer. So c had to be square root of an integer. It was c squared which was quantized.
Was for c squared.
C squared, right. So c was quantized up to square roots. Okay. Another small example would be that you take any simple gauge algebra with one hyper in the adjoint representation. So remember that the vector multiplier and hypermultiplier were just negative of each other up to the trace in the representation. Since the representation is now adjoint, you find one loop anomaly vanishes. You don't need any Green-Schwarz contribution. You don't need any tensor multipliers for this theory to be well defined. So this theory satisfies the first condition, right? Obviously, second. Okay. So I should say G is not SU2, SU3, or G2, and it satisfies. Right? Even in those cases, I think it satisfies the second condition, and it satisfies the third condition trivially as well. So, and yesterday we saw this theory. This appeared as n equal to 1, 1 little string theory, whose low energy limit was a super Yang-Mills theory without any tensor multipliers.
Unexpected symmetry enhancement. It's like n equals 4. So it's an enhanced to 1, 1, you're saying.
Right, right. Enhance 1,
Yeah. No, it's just 2, 1, 1. Yeah.
So on the tensor branch, it looks like a simple gauge group, gauge algebra with a one hyper in adjoint. And I was saying that the one loop anomaly polynomial vanishes, and there were three conditions that I was basing my classification on. The first condition was that the one loop anomaly polynomial should factorize as a sum of squares, a negative definite sum of perfect squares,
So that
which it trivially satisfies.
Something else.
Yeah.
Yeah.
The second statement was about global anomalies, which is satisfied in this case, and
Very briefly, what was the second statement, please?
that global gauge anomaly should also vanish. Then anomaly for pi 6g.
Okay.
And the third statement was about quantization of the coefficients appearing here, which is trivially satisfied.
So this is just what dimension reduction of, this is the 2B theory.
Right, this is 1, 1 latest string theory. Right.
Which at low energies is just.
Is this tensor branch? Yeah.
Uh,
On the tensor branch, it is this theory.
Is this the theory which the type 2B NS5 planes go to?
Right.
Type 2B in flat space.
Right.
Okay.
How many tensor multiplets are there?
No tensor multiplets because you just don't need them to cancel the anomaly.
There's no tensor multiplet. So even in the first example, there was no tensor multiplet.
There was a tensor multiplet because it was -4 times something, right? The anomaly polynomial did not vanish.
Okay. So from here you read out the number of tensor multiplets.
Right. From the number of perfect squares.
So this is where the different sums come into.
Yes.
Different terms in the sum come into picture.
Yes.
The AI and VI.
Yes.
Here there was only one term in that I8, so it corresponds to one tensor.
Right.
First example.
In the first example, yes. Okay. So now let me move on to the F theoretic classification. So our strategy would be to compactify F theory on a.
I'm sorry, I had to go. But so what was your conclusion from this? You gave some conditions, and did you try to classify all the branches that met these conditions?
Yes. And then I was discussing some examples, some simple examples where these conditions are fulfilled and how we saw them yesterday.
And your matter was it only bifundamental kind of?
Yeah, in this example, yes, but in the full general classification, you can include any sort of matter.
Okay. And do you have string theoretic constructions of all of these examples?
F theoretic constructions, yes. Okay. Okay, so now before moving on to the F theoretic classification, let me review some aspects of F theory, and I want to focus on the things that were left out in the original classification. There was a classification of due to Heckman, Morrison, Rodriguez, and Waffa, and it turned out that if you match the list of the Lagrangian theories with their classification, almost all of the Lagrangian theories will be found in the classification, but some particular theories were not found. So let me give those examples. So one would be an SU-SO bifundamental. They could not construct this in F theory. And another class of example had SU with symmetric hyper. So hyper in symmetric representation. So these were the two main classes of examples they could not construct.
I don't know what the original classification, or what's the original classification based on?
Right, so it was based on F theory. In F theory, you would look for, there were some consistency conditions, and you classify all the 6-dimensional compactification manifolds on which you need to compactify F theory to produce 6-dimensional theories. And they classified all these manifolds, and they could determine the tensor branch of vacua of each of these theories directly from the properties of the compactification manifold. So if you were to match the list of these tensor branches with the tensor branches in their paper, you will find that these two theories were here in this classification, but not in F theory. So you might imagine that there is some sort of there's some problem with these theories. They satisfy the consistency condition, but maybe the low energy theory needs to satisfy some more consistency condition for it to be an actual SCFT.
I remember in that paper they talk about some
Right.
stuff, right?
This is different from that. I'm just looking at.
But how does it fit into the arguments that you laid so far? I mean, you didn't raise a possibility of such a piece.
Right.
So even in the tensor branch, you could see some non-Lagrangian.
So the main example for this is DD conformal matter, right? And so this is a conformal matter with SO and an SO. Here you, instead of having a bifundamental of SOs, you have a CFT which couples to two SO flavor symmetries. Right. I mean, this is what they call as DD conformal matter. This is a CFT which has two flavor symmetries, two SO flavor symmetries.
And this CFT by itself does not have a tensor branch.
It has a tensor branch.
So now when you go to that tensor branch,
Then it becomes an SO SP, right?
so Lagrangian theory.
Yes.
But I thought your philosophy was to actually kind of simplify the theory by going to the tensor branch and just look at the Lagrangian.
Right. Only the Lagrangian ones. But this
I mean, in the limit where the tensor branch parameters approach 0,
you will obtain SCFTs, in particular DD conformal matter and other conformal matters.
So this discussion includes all the strong coupling physics also in the limit.
So it does not include EE conformal matter, for instance. That contains some strings which do not have, which are not instantons. So this one will construct for you only DD conformal matter. Okay, yeah. Right, so I was saying that if you were to match the tensor branches obtained here with the tensor branches in their paper, you will find that these two models are not realized in their paper. And you might imagine that these two models actually do not exist because it seemed like their classification covered almost the whole list, but just these, not these two. Now, ironically, I can give you a type 2A construction for these two models. So let me give you that one. So in type 2A, you can have, let's put some D6 branes with an NS5 brane in between. And let me put an O8. So I have some D6s, an NS5, which is submerged in the world volume of D6, and an O8 plus. Let me write down the directions for these branes. So D6s are stretched from 0 to 6, and O8 is stretched right. Okay. So now, yesterday I told you that there was some, anyway, right, so let's see what this theory will be. So there will be, let me put another NS5 here. So I will get an SU group coming from here. And from here I will obtain, there will be some action of O8 plus, of the orientifolding action on the Chen-Paton factors here. And it turns out that you obtain, in this case, SO. And so you can construct, and the strings in between will give you SO-SU bifundamentals. So here you have a type 2A construction which constructs this theory, which was not found in a theory.
D6 is infinite in that direction,
Right, it's infinite.
so that's just a flavor symmetry.
That's just a flavor for SU. And the second one also has is very similar construction. You just put this O8 on top of the NS5. So from here you get an SU, and from here, instead of getting fundamental matter, there is a projection due to the orientifolding action, and you obtain a symmetric matter.
Plus gives the symmetry.
Yes, the plus, O8 plus. Okay. Now the question is, the F theory is dual to string theory by various dualities. So why aren't these theories seen in F theory? So it turns out that they actually forgot to include O7 plus brane in the classification, and throughout the whole literature of F theory in the last 20 years. So that's what my plan is. My plan is to first present the classification as it is, along with the classification for lattice string theories, with the assumption that there are no O7 plus throughout the setup. And then I will show you how to incorporate O7 plus plane to construct these kind of theories as well.
Is there a reason why they didn't?
So the reason is that the O7 plus, why they did not consider O7 plus? Yeah, so when we were doing this analysis, it seemed like all of the nice rules for F theory were breaking down when you include O7 plus. And you won't be able to do classification. So we were not able to finish the classification. The rules got very complicated when you include O7 plus. So it just seems like it was very complicated and people just wanted to keep things simple, and so they ignored it.
So once you include this additional piece, you get even more theories than what the Lagrangian.
Yeah, you should, yeah.
What would happen maybe you get O8 minus instead of O8 plus?
So you get antisymmetric matter here, which was in the classification.
It wasn't the classification.
Yeah, so they included O7 minus.
It was
And
just O7 plus, which was.
the plus one was not included. Okay. Another caveat that I want to mention about this gauge theoretic classification is that there actually are additional consistency conditions that we don't know on the gauge just on the gauge theoretic, in the gauge theoretic examples as well. So this was demonstrated in a paper by I don't know how to. So Ohmori, Shimizu, Hachikawa and Yonekura. And the example that they were looking for had an SU2 gauge group with some spinor matrices that you have SO7, right? So an SU2 gauge group with an SO7 flavor symmetry. And this example, this exists in the Lagrangian case, but they showed that if you were to compactify this down to 5-dimensional 4 dimensions, then the Higgs branch of this theory will not be consistent with the Higgs branch that you expect in 5 or 4 dimensions from the compactified theory. And since Higgs branch does not depend on dimensions, this was a contradiction. So they found some problems with this theory.
By the way, once you specify the gauge content, matter content, representation, and so on, the Lagrangian is fixed, right? There is no superpotential type of
No.
interaction that you have.
These are the 8 supercharges.
Right. So then the flavor symmetry is not quite in your control, right? You should just say that SU7 with a bunch of fundamental flavors,
Mm-hmm.
and then whatever the flavor symmetry is what is the flavor symmetry that
Right.
you're left with.
Right.
So it's
So here you had some spinor matrices that you had SO7 flavor symmetry.
a doublet, right? If you have a doublet, you are saying 7 doublets will
So
give
he-
you SO7.
Right, so what do I want to do? Right? Is
Seven
spinor
power
here
SO7.
and a fundamental here. So it's fundamental tensor with spinor of SO7.
No, you cannot quite say spinor of SO7. That means you're choosing a subgroup to look at.
Right, so let me
You
change
can
my,
only specify
my
representation
example,
with
right?
respect to gauge group.
Right. So let me make it gauge. This theory also has a problem. Whatever is the flavor symmetry for this theory. Okay.
So that's SO7 is only subgroup of the flavor symmetry.
Of the flavor symmetry of this theory, yeah.
So, I just want to understand again the nature of the problem. So at level of Lagrangian it looks okay. All anomalies cancel.
Right.
But when you compactify, something goes wrong.
Right.
And say again what goes wrong, please.
So, right, I don't fully recall, but I think that when you compactify to 5 dimensions, you just look at the resulting theory, and you want to look at the Higgs branch of this theory.
I was just wondering whether, suppose you took a 2-dimensional conformal field theory,
Mhm.
before in it without including the twisted sectors.
Okay.
So if you looked at it in R2, it looks perfectly okay.
Right.
But then you put it on a torus, and you see that it doesn't have modular invariance.
Right.
I was wondering if it had the same flavor to that. I mean, is it a theory that would, for the conformal, in the conformal bootstrap on R6?
On R6,
Just
right?
look perfectly okay. Do you think?
I'm not sure. I'm just sure that the tensor branch satisfies these conditions. There are no anomalies, and it satisfies quantization condition.
Okay, thanks.
But there are the classification of just supersymmetric theory, like conformal symmetry is not visible at this stage. So
Bootstrap, yeah. But do you think that it is a theory that would have correlation functions on R7? That would obey all the axioms of correlation functions. It would just be a problem of
interesting topology.
Yeah.
The test also is about cycle compactification.
Yeah.
Right. So in the two-dimensional case, these theories produce for you a vector space, right, as a partition function. If you did not include the twisted sectors, and the twisted sectors are a way to get a partition function out of it.
Depends on which cycle you chose as.
Right.
It would not be.
But there are choices. There's a discrete torsion. There are choices in choosing these twisted sectors to get out a partition function, right?
Partition function. But if you just choose no twisted sector, let's say.
Then you get a vector space of possibilities.
Yeah, you get some partition function that depends not just on the torus but on a cycle.
Right. And then modular transformation acts on this vector space. So in that sense, all of the theories that I have been talking about so far have a vector space of partition function. They're not genuine theories.
Why do you mean?
So they are. I mean, their partition function depends on some extra choices.
What extra choices?
So this is about some choice of Lagrangian in H3 of the manifold.
I think this is all these things are like. I think this is the statement about pure gravity anomaly. So this is like the chiral WCW model, where a partition function of that would give you a conformal law, which would get acted upon by the modular law. Because it's not a pure two-dimensional theory; it's rather a boundary theory of a three-dimensional thing. Is that what you're saying?
Right.
This should be thought of as a boundary theory.
Boundary theory of a
So
seven-dimensional
there's a
theory.
statement about I think gravitational anomaly. But the mixed two is also probably.
I see. You're saying that in string theory, you have not just the surface, but the surface is in some particular space. There's some anomaly inflow.
There's an anomaly inflow.
Right. Fine. So really, in some sense, you can fill up the space. Like the bulk actually fills up the space. In the real theory.
So these are boundary theories of
Yeah,
some
in
topological
some
theories.
sense, Yeah.
So I don't know how to, because then now this.
Yeah. This is but it's even worse.
Yeah.
But then, I mean, this is a bit weird, strange, because if this is the case, that what you're passing on is boundary theories, then one could a priori allow for seven-dimensional Chern-Simons terms,
Right.
and then anomalies.
Some
anomaly-
seven-dimensional topological field theory.
Then your anomaly conditions would be modified.
No,
Because you were cancelling gauge anomaly by itself, but
Right.
if there is anomaly inflow, then you need not cancel it, but set it to the level of Chern-Simons, something like that.
Right. If you want, you can do that, right? But the seven-dimensional theory will have gauge sector in it.
It could. I mean, basically what I'm trying to
Right.
understand is the exact statement. If
Right.
it is the boundary theories that you are classifying, then
Right.
in the bulk there could be interesting topological stuff, as you said.
Right.
And all these gauge groups that you are talking about, the bulk theory could include their Chern-Simons counterparts.
Mm-hmm.
And if so, then the anomaly cancellation
Yeah, I see your point.
condition for these gauge groups on the boundary would be modified.
Right.
Perhaps you don't want to include the gauge
Gauge degrees of freedom in the seven dimensions.
But
gravitational Chern-Simons.
isn't it usually the case that bulk Chern-Simons gauge groups correspond to global symmetries in the boundary, rather than gauge symmetries in the boundary?
Depends on the boundary condition.
Yeah, I suppose.
Yeah, I mean,
usually not allowed.
Which thing is not allowed?
What Abhijit had in mind, I think, is that in a three-dimensional boundary and a four-dimensional bulk, if you put Dirichlet boundary conditions on the boundary, then a gauge
Then you
group on the
obtain a
bulk
global group.
becomes global.
Right.
If you add a Chern-Simons term on the boundary
Mhm.
and take K to whatever, strongly coupled,
Mhm.
zero, it becomes, which becomes Neumann boundary conditions. A gauge group at the bulk is a gauge group on the boundary.
Mhm.
But I think that may not be possible in this way.
No, I thought he was talking about 2D, 3D correspondence, where
Well, that's even lower dimension. So it's
Right.
true that at low enough dimension this is allowed. It may not be possible.
so if you have a gauge theory in any dimension, you can always have Dirichlet and Neumann, right? That there are always these two boundary conditions.
There are always these two boundary conditions. This is right.
But this is not the CFT anyway, so.
Yeah. But you know the Neumann boundary conditions in three-dimension boundary corresponded to strongly gauging the theory on the boundary with the Chern-Simons gauging.
Mhm.
You see, sorry, I agree. This is a bit of side issue. Let me just say. Suppose you take a global symmetry and you gauge it with respect to angles.
Mhm.
Then you're introducing new operators into the gauge, into the boundary theory. So that's not just changing some boundary condition, because that will be new fields in the bulk.
Mm.
Right? So you can't go from global symmetry on the boundary to gauge symmetry on the boundary just by changing boundary conditions, because you've got new operators and therefore new fields in the bulk in context of SCFT, unless the gauging does not introduce new operators. There's one situation. The context.
I don't understand why you need new fields in the bulk.
Because if you've got a new, according to SCFT, for every operator on the boundary,
Right.
there's a field in the bulk.
So here you're talking about the bulk of ADS-CFT and not the bulk in quantum field theory?
No, bulk of SCFT.
Okay,
So it'll be like your situation. Like
Okay.
you've got
I see.
a boundary theory and a real bulk,
Okay.
a gravitational bulk.
Uh-huh.
Okay, so if you've got suppose I compare the theory where you've got global symmetry and I gauge it.
Mhm.
If gauging introduces new operators, then the bulk theory has to be substantially different, because there are going to be new fields corresponding to the new operators.
Right.
However, if you manage to gauge in a way that it does not introduce any new operators, then you can there's possibility that you're getting away with just changing boundary conditions.
Mhm.
Okay, so in a situation like Chern-Simons gauging, you're not introducing any new operators, or maybe something else in two dimensions.
No, but I think even in 3D, 2D, in 3D bulk and 2D, you can have a Chern-Simons interaction in the bulk and just impose a Neumann boundary condition to the gauge field on the surface.
But once again, in 2D, a gauge theory has gauging introduces no new operators, because F is just determined in terms of matter. Okay, but in 4 dimensions, if you've got a Young's kind of gauging, then there's new gauge invariant information in the gauge field. I mean, it's just a statement that gauge fields are not
Right.
dynamic in 2 and 2 dimensions or 3-dimensional with Chern-Simons. You've got new dynamics, you've got new operators, and they've got new bulk fields.
Sorry, but here the comparison is between the gauging that you do purely on the boundary and the gauging that you do via bulk. So in any counting, the new fields were present in the bulk already.
No, what I wanted to do is compare the theory where you've got, let's say I've got a boundary theory, where I've got a global symmetry.
No, let's say gauge symmetry. But now the second scenario is where that gauge symmetry results from the bulk, Chern-Simons.
Okay. I'm just saying that changing Neumann to Dirichlet boundary conditions will not be just turning a global symmetry into a gauge symmetry.
Okay.
That's
But in this case, you agree, right? I mean, here the gauge symmetry is already present in the boundary theory.
yes.
The question is whether it could also come from some Chern-Simons term in the bulk.
Yes.
So one scenario is there is a Chern-Simons term with Neumann, and the other scenario there is no Chern-Simons term.
Yes.
In those two scenarios, there is no additional operator in the bulk.
Yes.
No field in the bulk.
Yes.
But the anomaly conditions are changed.
Yeah.
Right, so the statement is that there are no Chern-Simons terms in 7 dimensions, gauge Chern-Simons terms, because anomaly can be viewed as itself as introducing a 7-dimensional theory, right, just by descent.
Yeah, but could be topological. Can be topological.
Right, topological field theory in the 7 dimensions. So you can gauge a theory which has a global, suppose a theory has a anomaly in global symmetry, you can gauge it by going to 1 dimension higher, and which also has the global symmetry, and gauging the whole system.
Choice of an element in H3 which you mentioned,
Right.
that can be incorporated by extending it to a 7-dimensional bulk with the Chern-Simons term. That was how the discussion started.
Right,
Choice
right, right.
Choice in H3, what is
That
it?
was some gravitational Chern-Simons term.
But that was restricted to be a global symmetry in the field theory, right?
So I would say that you have this 7-dimensional theory which comes attached to this 6-dimensional theory, some gravitational Chern-Simons kind of 7-dimensional theory. And if you want an actual theory, you need to give a next boundary condition for it.
Right. So
To get a
that is
6-dimensional
global
theory.
symmetry on the boundary case.
I think it's just the case of non-vanishing gravitation anomaly.
Right, where the gravitational physics on the boundary is just global, right? That's not made dynamic. So that would just correspond to gravitational Chern-Simons in 7 dimensions with Dirichlet boundary conditions at the boundary.
So I don't think it's just gravitational anomaly. If there is gravitational anomaly, you can cancel it by 7-dimensional term, right? But even if you don't have gravitational anomaly, you can the theory will still be relative. There is some extra choice, some discrete choice involved,
Even without.
gravitational anomaly.
What is this extra? What is the extra choice?
It's similar to the story in 2,0. So 2,0 comes from NM5 branes, right? So that gives you a UN 2,0 theory. But if you include the center of mass motion, if you throw away the center of mass, then you are left with a relative theory, the SUN 2,0 theory.
Yes.
Right, so so as far as the discrete choice is concerned, I think it has to do with choosing a charge, right? So the 6-dimensional theory contains codimension 4 surface defects, and you need to, and there will be some charge lattice for these defects. There are strings as well, so you want these defects to be to satisfy Dirac quantization with these strings, right? Imposing this Dirac quantization, it turns out that you need to restrict the charge lattice, and restricting this charge lattice.
There are different ways of restricting it.
There are different ways. There are different solutions, and they're parameterized by H3 of the manifold.
Yeah, what operators are allowed? That kind of.
Right, right.
And if
So it's like the
It's like the Seiberg stuff.
Tachikawa, Seiberg,
Yeah.
Aharoni.
So if we choose something that's not allowed, then we need the 7-dimensional bulk for the whole system.
Right.
No.
So if you don't make a choice, then you have to introduce this topological field theory.
But just about the last discussion, at least in all the examples, the SUN gauge theory lived on D6 branes, which didn't extend into the bulk. There wasn't like an SUN gauge field in the bulk.
Okay. You mean in 6 dimensions?
In your examples of constructions of little string theories, your gauge theories lived on some D6 branes,
Right,
and then the bulk, the closed string sector didn't know about these D6 branes.
right.
Whereas the closed string sector certainly knows about gravity.
Mm-hmm. Right. Okay, so I will follow up with the F theoretic classification tomorrow, but let me set up by some review of F theory. So now, so D7 brane in type 2b theory has couples magnetically to RR scalar of type 2b, which means that when you have D7 brane and you go once around it, it induces a monodromy for the complexified coupling constant of type 2b. And this monodromy sends you from the perturbative sector of type 2b back into itself, because it does not affect the G string.
Now, luckily, I know almost nothing about F theory, so you'll have to go slow here.
Right.
This tau is made out of string coupling and axiom. Is this
Right.
And the statement that is just that the D7 brane is charged under the axiom.
Right.
That winds once.
Right.
And and the dimensionality is that 7 brane is codimension 2, so just a vortex of the axiom.
Right. And this monodromy keeps you within the perturbative regime. It does not influence
Because
the
it
G string.
affects only the axiom and not the string coupling.
Right. So this is the reason that you can see this 7 brane in perturbation theory.
Okay, good.
Now F theory says that in general you can include more general 7 branes, not just the D7, which are defined by the fact that the monodromy around them is some tau prime, some SL2Z on tau prime, SL2Z action on tau prime, or on tau. And since SL2Z is a duality of type 2b, you come back to type 2b again. In general, they can map you from perturbative to non-perturbative regime of the theory.
Like tau goes to 1 by tau.
Right. Yes. And now, so a way to think about these 7 branes is that you interpret this exodilaton as the complex structure of an elliptic fibration, since it lives in the upper half plane and has SL2Z monodromies. So you introduce 2 new directions, a torus over each point in space-time, and you just say that the complex structure of this elliptic fiber will be the tau at that point in space-time.
So as one goes around the 7 plane, this torus, the shape of the torus changes.
The torus gets a monodromy. Okay. Right. So now for very big, nice class of elliptic fibrations, you can write down a Weierstrass model for it. Which so here f, x and y are coordinates on CP1, and z are the complex coordinates on the base on the type 2b spacetime, and f and g are some functions which on the base. So if you were to take globally f and g will be sections of some line bundles, and locally they're functions on the spacetime.
So just to understand it in the original D7 story, so the transfer space is 2-dimensional for the D7.
Right.
So the total space of the vibration will be 4-dimensional.
It will be. It can be anything. I mean, it will be 12-dimensional.
For the transfer space.
In this particular case,
You can have 7 branes in all directions, right? I mean,
Let's say we choose 1 7 brane.
right.
In that case,
Then you need you have a 4-dimensional problem.
4-dimensional.
Right.
And the particular torus which corresponds to so to get different D7 branes, we can special examples choose different vibrations over this 2-dimensional space. That's the Weierstrass model.
Right. Right. And now the 7 branes, the location of the 7 branes will be the locations around which the elliptic fibration has a monodromy. So at the location you will have some singularity in the elliptic fibration. And since the elliptic fibration is defined by an equation, the singularities in elliptic fibration are just captured by the discriminant of this equation being 0. So you take the discriminant, right. So the places which solve this equation are where your 7 branes are located.
Sorry. So we've got y squared is equal to what? That's
X cubed, right.
So this is a polynomial.
So x and y are in CP1.
So x and y are making up the torus,
Right.
and z is the plane on which your torus.
Z is space-time.
Okay, z is space-time, right?
Complex coordinates on space-time.
Yes, and you're saying when this becomes a degenerated torus,
Yes.
that happens when what?
Those are the location of 7 branes.
When f squared.
When 4f cubed plus 27g squared is 0. The discriminant of this equation
Okay.
is 0.
Okay. And if I think of so there are two cuts in this. How should I think of this plate? Can I think of this if I solve for
As
y,
there. Two cuts.
Two
Right.
cuts,
Right.
and these cuts come touch
Together.
each other. Something,
Right. Yes.
So two roots. I see.
Yes. Right. Okay. So in general, the expectation in F theory is as follows: that you can. So mostly you restrict yourself to Weierstrass models, and then you say that 7 branes are in one-to-one correspondence with codimension 1 singularities of elliptic fibration. The intersection of 7 branes is in one-to-one correspondence with codimension 2 singularities, and so on.
In this Weierstrass form, the complex structure of the torus is just the argument of f and g, right?
So the complex structure will be something like g over f up to some factor. Right. So now if you just focus on codimension 1 singularities of elliptic fibrations, then these were already classified by Kodaira long ago. So let me reproduce this classification here. So the singularities are of the following type. They are given some names in the mathematics literature. You call them type IK, type 2, 3, 4, and their start versions.
Sorry, I'm sorry to be so totally ignorant, but for
Right.
these general branes, can you write down supergravity solutions? Or they just won't be reliable because of coupling constant?
They won't be reliable. You can write it down for IK and IK star. They are in the perturbative. These are the D7 branes, and this is O7 minus, and a stack of O7 minus and D7 branes.
Right. But forgetting about reliability, could you just write down the solutions anyway? Or they don't exist because you have to identify fields.
Right.
Yeah.
Okay. So let me make a table for these singularities. Here is the SL2Z monodromy for these singularities.
But I'm sorry again. Just in supergravity, suppose you treat tau to be a period, you allow identifications of tau. Then can you write down supergravity solutions too? Just
So
ignore
what
the
do you
fact about whether they're reliable or not. Try and
Right.
solve the supergravity equations with this winding.
But there is an electromagnetic duality going on, right?
I just allow tau to be to be multivalued. You're saying
Right.
it's not just that? Suppose I look for a solution which tau has a particular multi-valued.
Right.
Can one find such solutions?
Yeah.
Yeah, but that means that the fields have to be identified with the electromagnetic pair, right? Electromagnetic dual of those fields.
And what is the electromagnetic dual? Sorry, where is electromagnetic dual going at?
Because this is an SL2Z transformation.
So like an
It's a-
right.
SNS duality.
Right. So suppose you allow that. You allow multi-valuedness up to this transformation.
Okay.
This is something so basically you're saying that the solution is not single valued, but there's a particular kind of boundary condition as you come around.
Okay. Right. No, I don't know whether this has been done. Okay. So okay, so here in the table I'm plotting the singularities versus some of their properties. Order of f means the order of vanishing of f as you approach the singularity, and similarly order g and order delta mean the order of vanishing of these functions as you approach the singularity.
And sorry, in these 7 branes you say this axion is sort of rotating around at infinity if you have one of these 7 branes.
Right.
So the physical, if you're really interested in just excitation.
No, not infinity, around it.
But also
D7.
at infinity. If there's just one 7 brane.
Right. So it's also at infinity.
So, but if you really want something, you want something with a given boundary condition at infinity, you consider a brane and its antipartner or something like that.
So you don't want multivaluedness at infinity?
Let's say that I want my infinity to be normal boundary conditions.
Right. So you mean anti-D7 brane?
But that would break supersymmetric. Oh, you want to put them on compactification or something?
Yeah, I want some supersymmetric configurations.
Okay.
And it can be non-compact compactification as well.
I think this is K3 story, right?
So there is no notion of G string.
Are you going to be long?
Oh.
Yeah,
Can you finish
Okay.
after 2 minutes?
Okay. Okay, then I can write the classification tomorrow.
Sounds good. Yeah.
Okay.
The K3 story is that the K3 itself carries some charge.
No, K3 is you're studying elliptic vibrations on sphere, and so that's the compact.
That's a compact manifold.
Manifold, right?
So the flux
So that's like
of the 7 branes.
Single boundary conditions, and then you want to see what sort of singularities are allowed. I think this is 24.
24 of them.
Because there's some charge you have to cancel.
Yeah.
Right.